So, good day everyone. Today we're going to discuss the Avl tree and how it works. So, what is an Avl tree? So, an Avl tree is another balanced binary search tree. It was the first such data structure to be invented. So, AVL was named after their inventors, Adelson, Belsky, and Landis. So, they were the first dynamically balanced trees to be proposed. So in an AVL tree, the height of the two child subtrees of any node differ by at most 1. So if at any time they differ by more than 1, and rebalancing is done to restore this property. So AVL trees have the property of dynamic self-balancing in addition to all other properties exhibited by binary search tree. So a BST is a data structure composed of nodes and it has the following guarantees. First is each tree has a root node at the top. The root node has 0, 1, or 2 child nodes. Each child node has 0, 1, or 2 child nodes. And each node has up to 2 children. So for each node, its left descendants are the less than the current node, which is less than the right descendants. Enable trees have an additional guarantee. The difference between the depth of right and left subtrees cannot be more than 1, and this difference is called the balance factor. So to maintain this guarantee, an implementation of an ABL will include an algorithm to rebalance a tree when adding element will upset this guarantee. So ABL trees have a worst case lookup insert and delete time of O log n, where n is the number of nodes in the tree and the worst case space complexity is On. So when we say balance factor, the balance factor of a node in an AVL tree is the difference between the height of the left subtree and that of the right subtree of that node. So balance factor is equal to height of left subtree minus height of right subtree, or height of right subtree minus height of left subtree. So the self-balancing property of an AVL tree is maintained by the balance factor, and the value of the balance factor should always be negative 1, 0, or positive 1. So for instance, here we see that the first tree is balanced and the next trees are not balanced. So in the second tree, the left subtree of C has a height of 2 and the right subtree has a height of 0. So the difference is 2. Next, in the third tree, the right subtree of A has a height of 2 and the left is missing. So it is 0 and the difference is 2 again. So AVL tree permits the difference balance factor to be only 1.
Next is the height of an ABL tree. Proof. Fact. The height of an ABL tree storing NK is O log n. Proof by introductions. Let us bound NH, the minimum number of internal nodes of an ABL tree of height or h. For n is greater than 2, an ABL tree of height h contains the root node, one ABL subtree of height n negative 1, and another height n is negative 2. If there are n nodes in ABL tree, minimum height of ABL tree is floor log n base 2. If there are n nodes in ABL tree, maximum height can exceed in 1.44 multiplied by log n base 2. Next is the ABL insertions. Insertions is an ABL tree similar to insertions in a binary tree. But after inserting an element, you need to fix the AVL properties using left or right rotations. If there is imbalance in the left child right subtree, perform a left-right rotations. And also if there is an imbalance in the left child left subtree, perform a right rotations. If there is imbalance in the right child right subtree, perform a left rotations. And if there is an imbalance in the right child left subtree, perform a left rotations. Insertions is an AVL tree performed in the same way as it is performed in the binary search tree. The new node is added into AVL tree as a leaf node. However, it may lead to a violation in an AVL tree property. and therefore the tree may need balancing. The tree can be balanced by applying rotations. If the difference in the height of the left and right subtrees is more than 1, the tree is balanced using the sum rotations technique. In AVL trees, after each operation like insertions and deletions, the balance factor of every node needs to be checked. If every node satisfies the balance factor conditions, then the operations can be concluded. Otherwise, the tree needs to be rebalanced using rotations of rotations. There are some rotation techniques to balance itself. An ABL tree may perform the following four kinds of rotations. First, it has the left rotations. Second, right rotations. Third, the left-right rotation, and also the right-left rotations. In AVL 3, after each operation like insertion and deletions, the balance factor of every node needs to be checked. If every node satisfies the balance factor condition, then the operation can be concluded. Otherwise, the tree needs to be rebalanced using rotations operations. The first two rotations are single rotations, and the next two rotations are double rotations. To have an balanced tree, we at least need the tree of heights too. With the simple tree, let's understand them one by one. First is the left rotations. How it works. So if a tree becomes unbalanced, when a node is inserted into the right subtree of right subtree, then we perform a single rotations. In our example, node A has become unbalanced as a node is inserted in the right subtree of A's right subtree. We perform a left rotation by making a left subtree of B. Another advantage of using a left rotation is that it fixes the given value in the AVL tree by relocating the element A so that it becomes a child of the root, which is the B. Therefore, by arranging the elements A and C as children of the root node B using the left rotation, it makes the tree balance.
ABL tree may become unbalanced if a node is inserted in the left subtree of the left subtree. Tree then needs a right rotation. As depicted, the unbalanced node becomes the right child of its left child by performing a right rotation. We perform the right rotation by making C the right subtree of B. Left-right rotation. Double rotation are slightly complex version of already explained version of rotation. To understand them better, we should take note of each action performed while rotation. Let's first check how to perform left-right rotation. A left-right rotation is a combination of left rotation followed by a right rotation. A node has been inserted into the right subtree of the left subtree. This makes C an unbalanced node. These scenarios cause the AVL tree to perform left-right rotation. We first perform the left rotation on the left subtree of C. This makes A the left subtree of B. Node C is still unbalanced, however now, it is because of the left subtree of the left subtree. We shall now right rotation the tree, making B the new root node of this subtree. C now become the right subtree of its left subtree. The tree is now balanced. So, that is how we perform left-right rotation where every node moves one position to the left, then one position to the right from the current position.
Right-left rotation. The second type of double rotation is right-left rotation. It's a combination of right rotation followed by left rotation. A node has been inserted to the left subtree of the right subtree. This makes A an unbalanced node with balance factor 2. First, we perform the right rotation along the C node, making C the right subtree of its left subtree. Now, B becomes the right subtree of A. Second, node A is still unbalanced because of the right subtree of its right subtree and requires a left rotation. In this scenario, a left rotation is performed by making B the new root node of the subtree. A becomes the left subtree of its right subtree B. And last part is the subtree which is the tree is now balanced. Consequently, that is how we perform right-left rotation, where every node moves one position to the right, then one position to the left from the current position. Key terms: trees which remain balanced and thus guarantee O lag and search times in dynamic environment, or more importantly, since any tree can be rebalanced but at considerable cost can be rebalanced in O lag in time. AVL trees are beneficial in cases like a database where insertions and deletions are not that frequent, but you frequently check for entries. Take note that an AVL tree must be balanced, and every AVL tree is a binary search tree. This means that the depth of a node left and right subtrees can differ by no more than 1, and the balance factor should always be -1, 0, or +1 to keep an AVL tree balanced.
So here are references, and here are the group mates. And that's it. Thank you for listening. Have a nice day.